All right, so here we
I
go.
have come a long way.
Page 7 of our packet. We are not going to type these in. We'll just set them up. But you are free to go back and practice and get them typed in if you feel like you need that extra practice. All right, so here we go. We have a class of 10 students, 5 boys and 5 girls, and 1 teacher. In how many ways can the students sit in a row if there are no restrictions? 10 factorial. Now, it's going to be up to you as we rattle through these to say, whoa, 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 I don't get that. Okay? We want to get through as many as we can this morning. So everybody good with 10 factorial? How about in a circle? 9 factorial. Sit in a row if all of the boys sit together and all of the girls sit together.
2 factorial.
2 factorial.
5 factorial.
5 factorial. 5 factorial. Everybody okay with that?
Yes.
Sit in a row if the boys cannot sit next to other boys and girls cannot sit next to other girls. Oh, what does that mean? That means we're alternating, right? Everybody okay with that thought? So let's think about what that looks like. Here are the 10 kids. Now, my job is to seat them alternating, okay? How many choices do I have for the first spot right here? Whoa, 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 wait a minute. Can't anybody sit in the first spot? I have 10 choices for the first spot. Does that make sense to everybody? Okay, so now I gotta fill the next spot. Now how many options do I have here? 5, because I have whatever gender I didn't put here. So if that's a girl, there are 5 boys then that I could put here and vice versa. So there are 5 for that spot. Now what about for this spot? 4, because you're gonna put here whatever you put here. Does that make sense to you? So now I got 4 here. What about here? 4 because that goes here. These go together, right? And then 3, 3, 2, 2, 1, 1. Now what are you going to do with all those numbers? Multiply them together. You're going to multiply them together. Stand in a row for a picture if the teacher must stand on one end or the other. So we're going to line everybody up and all 10 kids in a row, and then the teacher is either going to stand on this end of the kids or on that end of the kids. What's your thought? Don't make it harder than it is. Think if we were really going to take this picture. We line all the kids up first, right?
Yeah.
How many ways can I line those kids up? 10 factorial. So there's 10 factorial ways if I'm on this end, the teacher's on this end, the teacher's here, there's 10 factorial ways to line the kids up. Well, what if I'm on that end? There's still 10 factorial ways with the teacher here. So isn't the answer just 10 factorial plus 10 factorial? Or 2 times 10 factorial? We're on page 7, Charlie. How many ways can we elect a president and a vice president from the students in the class? 10P2. Why is it 10P2? Different positions. 10 kids, 2 positions, and they are different. Select a king and a queen from the students in the class. The king must be a boy and the queen must be a girl. Think of it just like cards. You're picking a club and a jack or something, okay? So how many boys do you have? You're going to pick a king, right? So it could, when you're only picking one, it can be P or C. So it can be 5C1 or 5P1. It doesn't matter. If you're only picking one, obviously there's no order. So it doesn't matter. It's the same answer. They're equal to each other. So that would be the king. Now what would the queen be? Same thing. Since you are picking a king and a clean, you will multiply them. All right, same group of kids, but now, in how many ways can the teacher award 3 different prizes to individual students? Don't make it harder than it is, you guys, just because it's worded a little bit differently. Don't make it harder than it is. There are 3 different prizes, so that would be 10 P3. I's a little bit different. Award 3 prizes to students if a student can be a repeat winner. Now, what does that mean? That means I can give everything to my favorite student. Right here, Vega gets everything, right? Or I can give 3 individuals, or I can give 2 to you and 1 to you. Oh gosh, how are we gonna figure that out? How many ways can I give out the first prize? 10. Right, there's 10 kids. So the first prize can go out 10 ways. What about the second prize? 10. And the third prize? 10. And since I'm giving away prize 1 and 2 and 3, there's 1,000 ways that can happen. How many ways can I send the class hamster, rabbit, and gerbil home with 3 different students for the summer if 4 students have allergies and are not allowed to be considered? 6 C3 or 6 P3. 6 P3. So why 6? We threw out the other 4 kids, right? Why P? Different animals, right? 1 student is named Thomas. How many distinguishable arrangements of the letters in his name can be formed? Thomas.
6 factorial.
6 factorial. No repeat. 6 factorial. Another student is Cassandra. So question L, Cassandra would be 9 factorial because there's 9 letters.
Over 2 factorial, 3 factorial.
2 factorial for the S's. 3 for the A's. Is that it? So there you go. And I keep cautioning you about this. I'll try to stop. When you type this into your calculator, since there are 2 things in the denominator, make sure you put parentheses around it. 5 students get ice cream, the other 5 get spinach. How many ways can the 10 students be divided into the 2 groups? 10 C2? What would be your logic there, 10 C2?
It's 2 different groups, there's 10 groups.
Okay, but be careful. When you say 10 C2, you mean there are 10 kids and I'm just gonna pick 2 of them. That's not what we're doing, right?
There's 10, you're gonna get 10. 5 are gonna get ice cream.
Okay, so let's just wait a minute. Let's just do it one at a time. So there's 10 of you. 5 of you are gonna get picked for ice cream, okay? So how many ways can I do that? Forget the spinach. I'm gonna pick 5 of you for ice cream. How many ways can I do that? 10 C5. So 10 C5 is the picks for ice cream.
10 C5.
Now wait. It's not 10 C5 again.
It's 5
C5. Why is it 5 C5? Because there's only 5 kids left, right? Does that make sense to you? Where am I? In how many ways can all but one of the students sit in a circle with the 10th student sitting in the middle of the circle? Okay, now do not get freaked out by this. Stop a minute. I say to you, there's 10 of you in the room. I say to you, someone stand in the middle and everybody else stand around. Okay? So how many choices are there for the middle spot? well, there's only one middle spot, but how many kids could stand in the middle? 10, right? So you can do 10 C1 or you can just do 10, it's the same thing. There's 10 options, right, for the middle of the circle. Now, how many kids are left? 9, and I'm going to arrange them in a circle.
8 factorial.
So it's 8 factorial. So it's 10 times 8 factorial. Why 10? Because I got to pick somebody for the middle. Why 8 factorial? There's 9 kids left arranged in a circle. Okay? In how many different orders, important word, can the teacher schedule parent-teacher conferences for her 10 students if there are no restrictions? In how many different orders? Well, how many kids are there? 10. How many conferences do I need to schedule? 10. Does the order matter? Whoa, whoa, whoa. What's the question say? In how many orders can I do that? So it would be 10P10. 10P10. Thomas and Cassandra's parents will ride to parent-teacher conferences together. In how many different orders can the conferences for the 10 students be arranged if Thomas and Cassandra must have their conferences back to back? Okay, now, wait a minute, let's think about this. This is like arranging books on a shelf or kids. Yeah, these two have to be tied together. All right? So how many are there all together? Well, there were 10, but these two are tied together, so there are 9 factorial. Well, 9 now I'm going to arrange, so that would be 9 factorial times 2 factorial. Don't be confused by the wording. This is just another variation of bundling. These two have to be tied together, so now you have 9 things to arrange. That's 9 factorial times the bundle 2 factorial. In how many ways can the teacher choose 4 students to serve on the class council if there are no restrictions? Be careful. How many kids are there? No, I'm picking 4, but how many am I picking from? 10? I'm putting them on a council, so does order matter? So that would be 10C4. How many ways can the teacher choose 4 students to serve on a committee, and I must have 2 boys and 2 girls? Like a card problem. How many boys in the group? 5. I'm picking 2. 5C2 times 5C2. Because that's like the card problems where you have to have 2 hearts and 3 clubs or something. Is how many boys do you have? 5, you're picking 2. How many girls do you have? 5, you're picking 2. And the order doesn't matter. So 5C2, 5C2. How many ways can the teacher award identical prizes to 3 students? 10C3. How many ways can the teacher choose 4 students to serve on the class council if there must be exactly 1 girl? Exactly 1 girl. 5C1. There's 5 girls, so 5C1 times 5C3. 5C1 times 5C3. There's 4 kids on the council. 1 is a girl. The other 3 must be boys then, right?
How's it 5?
There's 5 girls and 5 boys in the class. Yeah, it says up at the top, there's 5 boys and 5 girls in the class. Now, how many ways can the teacher choose 4 students if there must be at least 1 girl? All right, now wait a minute. This is the ways that there's exactly 1 girl, right? What else could happen?
5C2, 5C2.
We could have 2 girls and 2 boys. we could have 3 girls and 1 boy, or we could have
4 girls.
all 4 girls. And these all get added up because it's 1 girl or 2 girls or 3 girls or 4 girls, right? What?
Because we started out with 5 girls and 5 boys. Oh, rich. It's like he already came with 5.
There's only 5 girls in the class. So if you're picking girls, John, look at the very first sentence at the top of the page. There's 5 girls in the class. So if I only have 5 girls to choose from, then that's the way I'm picking. One more. How many ways can the teacher choose 4 students if there must be no more than 2 girls? What does no more than 2 girls mean?
So, no,
Either be 1 girl.
There could be 1 girl, or there could be 2 girls, or there could be no girls, right? No more than 2 means 2, 1, or none. So 1 girl, we already did that. What does 1 girl look like? 5C1 times 5C3. Remember, you're picking a committee of 4. If you tell me, Miss Ford, there's got to be 1 girl, then that means there has to be 3 boys, if it's a 4-person committee. All right, so 2 girls. 5C2 times 5C2. There's 2 girls, 2 boys. What would no girls look like? 5C4. Well, yes, you could do 5C0 and 5C4. You absolutely could do that. You don't need the 5C0. If you're not picking any, you don't need to include that, but you can. It won't hurt anything. It's 1. It won't change anything. And then you're going to add those up, right? Because those are the different scenarios you could have.
So when you add them up, you just leave it like that, or you actually combine them?
Well, you're going to type that in on your calculator and get a number. You're going to get a number here, you're going to get a number here, and then you're going to add up those numbers. There's another way to combine them. You have to have the numerical values. W is a repeat question. What's the answer to W? We've already done this problem. It was worded differently. Instead of getting nothing, the other group got spinach, but it doesn't matter what I'm giving them, right? I'm grouping them the same way. So how did we say W worked? 10C5 times 5C5, right? How many ways can the teacher divide the class into 5 groups of 2, where each group will get a different snack? So that's like, 1 group gets spinach, the other group gets applesauce. 1 group gets ice cream, 1 group gets bananas. Does it really matter what I'm giving them? Yeah, right. That's what we could do, yeah. So what would the answer be? Just like ice cream and spinach, because 10C5 times 5C5. All right, now we're ready to go. How many, oh shoot, there's more. How many ways can the teacher divide the class into 2 groups of 5 where the groups will be treated the same? I turned the page. I turned the page.
Oh, we're on Y.
So now we're on Y. So Y would be 10C5 times 5C5. What would Z be? Now we're dividing them into pairs. So the first, so I'm gonna pair you up. All right. So first of all, how many kids are there in the room? 10. And I'm going to choose 2 at a time. 10C2. Now wait a minute. If I have done 10C2, does that take care of it? No, because now I have to pair up everybody else that's left. All right, I need to think about this for a minute. Hold off on that one. I need to ponder that for a second. Because I have two thoughts and I'm not sure which one's right. So hang on to that. Let's go on to the next question. I'll come back to that one. 5 cards are drawn from a standard deck of 52. How many 5-card hands have? All right, so we've changed scenarios. Now we have a deck of cards. We're picking 5. How many 5-card hands have all red? Guys, come on. How many red cards are there in the deck?
13.
No, red. Red.
Half. Right,
Oh,
right, half.
11.
It's half of 56.
I don't know.
It's half of 52.
26.
27.
There's 13 diamonds and 13 hearts, right? So there's 26. And how many are we picking? 5. 26C5. That is an easy question. Well, good for you, Griffin. Now, all 5 cards of the same suit. Now be careful. What does that mean?
All of them are like diamonds or all.
Oh, so right there, whoever was over there mumbling, you're right. It means all diamonds, or all hearts, or etc., right? Now, what would all diamonds be? 13C5. That's all diamonds. What would all hearts be? 13C5. And spades? And clubs. Right? So we could get this, or this, or this, or this. What am I going to do with those 4 numbers? Add them up. And since they're all the same, we could just say we have 4 13C5s if you wanted to simplify it a little bit. Exactly 2 red cards. Okay, in my hand, I have to have exactly 2 reds, so I heard 26C2. That's perfect, but you're not done. Times 26C3. Why do we need that? Because it's a 5-card hand. And if 2 of them are red, the other 3 have to be black. At least 3 aces. At least 3 aces. What does that mean? That means 3 aces or 4 aces. So what about 3? 4C3 times 48C2. Perfect. Where did the 48 come from? It's the rest of the cards that are not aces. Charlie, I want you to pay attention. That's what's up. Now, 4 aces. 4C4 times 48C1. And you're going to take those 2 numbers and add them because it's 3 or 4 aces. Oh man, he's a toughie. At least 1 card from each suit. Now, what does that mean? That means that every hand has to have at least 1 diamond, right? And at least 1 club, and at least 1 spade, and at least 1 heart, and then something else, right? All right, so let's do that. Let's look at that for a minute. How many ways do we have to have 1 heart and 1 diamond and 1 spade and 1 club and 1 other card? And we don't care what that other one is, right? So here we go. How do we get 1 heart? 13C1. And 13C1 and 13C1 and 13C1. Is that
C2.
And then it's,
now we got a problem though.
Why? C2 and another.
And another is a problem. Okay, here's the problem with the way I've started this. I've set up. I have split my deck into 4 piles: diamonds, hearts, clubs, spades. And I said I need 1 out of that pile, 1 out of this pile, and so on. This last card's problematic because I don't know what pile I'm going to. So I want to go back to the beginning. And would you agree that if you have to have 1 of each suit, you're gonna have 2 of something? So let's just say, what if I wanted 2 hearts? What if it was hearts that I wanted 2 of? And 1 of everything else? Then, if that were the case, then it would be 13C2. And then 1 diamond, 1 spade, and 1 club. So that would take care of if there were 2 hearts. Now, what would it look like if I had 2 diamonds? Wouldn't it be exactly the same thing? And 2 clubs would be the same thing, and 2 spades would be the same thing. So since it's 2 diamonds, or 2 clubs, or 2 spades, or 2 hearts, wouldn't I have this right here added up 4 times? Just in a different order, but I'd have the same numbers added up 4 times. So in other words, it's 4 of these. It's 4 of those. Because each scenario is identical. 2 hearts, 1 of everything else. 2 clubs, 1 of everything else. Those are all identical, and there's 4 possibilities. So you can either add them up 4 times, or you can just times it by 4.
So would you just figure out each one of those individually and then multiply them all together and then times it by 4?
Yeah. Yeah. There are 10 people at a party. Each person shakes hands with everybody else once. How many handshakes will occur? What's your logic on 10 factorial?
Because now, like, it doesn't ask for how many ways, like,
Well, yeah, if I'm gonna shake hands with you, that's like a pairing, isn't it? So, how many people are there in the room? And we wanna pair them up. It's like, remember the diagonal problem with the polygon? We want to connect 2 dots. So does it matter whether I shake hands with you or you shake hands with me? That order doesn't matter. 10C2. The answer is 10C2. You got 10 people, you're going to group them 2 at a time. Pair up every one. It's just like the diagonals of a polygon where you're connecting the points. Now we're connecting the people. 10C2. A fair coin, that means a regular coin, is tossed 8 times, and the result of heads, tails is noted on each flip. How many outcomes are in the sample space for this experiment? Do not make this a hard problem. It sounds much more complicated than it is. It's tossed 8 times. So, yes, 2 times 2 times 2 times 2 times 2, that's right. Here are your 8 flips. How many outcomes are possible for that one? 2, and there's 2, and 2, and 2, and 2. So the answer is 2 to the 8th power. It's 2 times 2 times 2, 8 times. Every outcome, or every flip has 2 outcomes. If you're doing it 8 times, first and second and third and fourth and fifth, you're going to multiply all those together. 2 times 2 times 2, and so on. In an urn, there are 6 red, 8 white, 4 blue. You reach in and randomly choose 4 marbles. How many ways can the marbles be selected so that all 4 are the same color? Okay, so all 4 the same color. What does that mean? 4 white, or 4 red, or 4 blue.
Does this have a 30?
Yeah. It was a little longer. That's good. We want to get this sheet done. How many ways can I pick 4 white marbles? What? AC4, perfect. AC4, there you go. Just like picking clubs out of the deck or picking girls out of the pile. You got 8 white marbles, you're going to pick 4 of them. The order doesn't matter, you just want to have 4 white marbles. How about, stop it! How about 4 red? How can we get 4 red? 64. 4 blue. What am I going to do with these 3 numbers? Add them up. It's one or the other. We're going to add them up. You reach in, randomly choose 7 marbles. How many ways can the marbles be selected so that at least 1 marble is white? Oh my gosh. What does that mean?
At least one, so it's 1 or 0.
At least 1.
Oh, so at least, so that's 1, 2, yeah, so.
1 or 2 or 3 or 4 or 5 or 6 or 7. Yuck.
Ew.
That's a lot of work.
Is there a way to simplify it or not?
There is. Let's think about this for a minute. Hey, you guys, this is cool. Think about this for a minute. Here's our dilemma. All right? Our dilemma is that we can do all these situations like we just did. There were 3 of them here. We did each one, added them up. We can do that again. The problem is there's a bunch of situations. 1 white, or 2, or 3, or 4, or 5, or 6, or 7. Doable, very doable. But let's stop and think about this for a minute. I reach in and grab 7 marbles out of this urn. I want at least 1 to be white. Is there anything else that could happen besides at least 1 be white? Will there always be at least 1 white one? No, what else could happen? There could be 0 white. But that is the only other case, isn't it? So instead of doing 1 white, 2 white, 3 white, 4 white, etc., I'm going to take the total ways of picking 7 marbles, and I'm going to subtract the ways of getting no white. Because everything else that's left, if I take all the total ways I could get 7 marbles, and I took out the ways that had no whites, then what's left? Some whites. 1, 2, 3, or so on. Now, how many total ways can I pick 7 marbles out of this urn? 18 C7. That's the total ways. There are 18 marbles in there. I'm going to pick 7. The total ways, regardless of color, would be 18 C7. Now, I don't want any whites. How many ways can I get no whites? That means they have to be red or blue. 10 C7. There's going to be the answer to the question. Now, that will be exactly the same as if you did 1 white plus 2 whites plus 3 whites and da-da-da-da-da-da-da-da down the line. This is called going through the back door. Instead of figuring out what you want, which is 1 or 2 or 3 or da-da-da-da, you take the total minus what you don't want. And a lot of times that's shorter.
Well, there's 7 white.
Huh?
So 18 to 10?
No, 18 there are 18 total marbles in the urn.
Okay.
And I'm going to pick 7. So if we didn't even talk about color, didn't think about color, there'd be this many ways to do it, period. There are 8 white marbles in the
there's
urn.
only 7, okay.
No, there are 8. If I take out all the white ones, then there's 10 left.
Yeah, so
right.
That's another 7 over there.
Yeah. All right. You have an unlimited supply of red and black jelly beans in a huge jar. You randomly choose and eat a jelly bean, and you continue to do this until you either eat a black jelly bean or until you have eaten 5 jelly beans. How many outcomes are in this sample space? All right? So here we go. You go to the jar and you reach in and you grab a jelly bean. What happens? It's either black or red. All right, so there you go. Now, if you eat a black one, you're done, right? It says you keep going until you either eat a black one or you've eaten 5. So if you eat a black one, it stops right here. But what if you eat a red one? You're going to eat another one, right? And that's going to be black or red. And if it's black, you're done. But if it's red, what's going to happen? You're going to eat another one. And again, you're going to eat another one. And again, you're going to, wait a minute, how many have I eaten? 1, 2, 3, so I'm going to eat one more. Black or red? So now your job is to figure out how many outcomes are possible. Well, the first outcome is you eat a black one. Done. The second outcome is you eat a red and then a black. That's an outcome right there. You're done. So you eat a red one and then a black one. What else could happen? You could eat red, red, black. What else could happen? You get the hang of it? You could do red, 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 black. You could do red, 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 black. And you can do red, 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 red. Those are your options. Those are your options. So how many outcomes are there? 1, 2, 3, 4, 5, 6.
I thought it said there's unlimited supply.
There is.
Supply demand.
But it says, Jack, it says you're going to keep doing this until you either get a black one or you've eaten 5. After 5, Mom says stop. A test has 15 true-false questions and 10 multiple-choice questions. Assuming that you answer all questions, in how many different ways could you do this? All right, so we've got 15 true-false questions, and we've got 10 multiple-choice questions. I'm not going to write out all those blanks. There's a lot of them. All right, so here we go. This isn't a probability question. We're not talking about how many ways can you pass. We're saying how many different ways can you answer. So this is a true-false question. How many options? 2. How many options for the second one? 2. And so on. So how many of those do you have? 15? So 2 to the 15. 2 times 2 times 2 times 2. Every true-false has 2 options, right? Now, what about the multiple choice? How many ways can you answer this? 4? 4, 4, 4. So that is, how many of those are there? 4 to the 10. Now, you're doing true-false and multiple choice, so you're going to multiply those together. Number 9. Yeah. No, it's almost time to go. You can go on the way. Okay.
What time is this out?
45, I believe. Yeah.
Wow, give me some love.
Before we go, we said what you can. All right, given a set with 10 elements, how many different subsets containing 5 elements can be formed? All right, what's your thought? Okay, some of you, and I don't know if it's because you just are sick and tired of me blabbing, if you have your mind on the assembly, I have no idea why you're this way. Stop a minute and think. This is exactly the same question as, I have 10 kids in the room, and I'm going to pick a committee of 5. It's the same question, 10C5. You have to be able to see the scenario for what it is. Not the specific problem, but the general overall sense. There are 10 people or 10 things, and you're picking 5 of them, order doesn't matter. So it's 10C5.
You love it.
All right, read number 10 and tell me what your thought is on that one. We have already done this problem. We've already done this problem. What is this exactly the same as? The jelly bean problem. Because what happens, instead of reaching in and grabbing jelly beans, what am I doing? I'm reaching in and grabbing light bulbs. And as soon as I get a defective one, as soon as I get a black one, I'm done. Otherwise, I keep picking, and I only pick 5. So it's exactly this, except it's defective and not defective, instead of red and black. Got it? Okay, so that takes care of that sheet. All right, the next sheet we have that I really want to do is page 10. So we will not get page 10 done, but next time we're together, we'll work on it. So somebody keep track of where we ended, or I'll try to keep track of it too. So here we go, we're on page 10. This is our in-class review sheet. Take a deep breath.
So 19.
Here we go. How many ways can 4 juniors and 5 seniors be seated in a row? 9 factorial. Now, same thing, we're going to seat them in a row, except each class has to be kept together.
9C.
That means all the juniors together. Reese? Oh, yeah, I haven't had a chance to think about it yet. I'll come back to it. All right, how many ways can 4 juniors and 5 seniors be seated in a row, each class together? This is number 2. 2 factorial, y, 2 groups, 4 factorial, 5 factorial. Chandler, wake up, please. Only the juniors are together. So we're seating them in a row, but only the juniors are together. 6 factorial, 4 factorial. Now, you got to engage your brain enough to ask if you don't get 6 factorial, 4 factorial. On a scale of 1 to 10, that's a 1 in terms of difficulty. We need to be able to do that kind of problem. That's easy. All right, number 4. How many ways can I give 5 identical prizes to my class of 21? 21C5. Repeat the problem, but now the prizes are different. 21P5. Number 6. How many 5-card hands contain exactly 4 hearts? 13C4. That would be exactly 4 hearts.
But you need one more.
I need one more. Very good, Griffin. Times what?
No, whatever.
39C1. Exactly 4 hearts means 4 hearts and 1 other card. Number 7 says at least 4 hearts. What does at least 4 hearts mean? 4 hearts or 5 hearts. And what would 5 hearts look like? 13C5. There you go. So the answer to number 7 is the answer to number 6 plus this. You had fun on the bus quiz like that. What is the probability of number 6? Okay, so remember, number 6 was 13C4 times 39C1. Those are the hands that have 4 hearts. Now turn that into a probability problem. It means you have to divide it by something. What are we going to divide it by? What? 52C5. And why are we dividing by 52C5? Because in a probability problem, the denominator is the total. How many total cards are in the deck? 52. How many total am I picking? 5. That's going to be your denominator. In fact, that will be the denominator for every 5-card hand probability problem, won't it? That's it. That's the denominator every time. All right, so we'll stop right there. Oh wait, let's do number 9 because it's so easy. Number 9.
Yeah.
How many ways can I arrange 10 people around the Celtic cross? 9 factorial. So I'm stopping right here with F. We'll pick up there next time. All right, anybody who wants to take a picture of today's schedule, I'm sure it was sent to you, but if you want a picture of it, there it is. And we are going to set as a